Hello everyone, today I will present Dynamic-eDiTor, a training-free framework for text-driven 4D scene editing with multimodal diffusion transformers. Our goal is to edit dynamic 4D scenes using only text instructions. As shown in the teaser, Dynamic-eDiTor supports diverse edits, including local appearance changes, object-level visual effects, and global style transformations. Importantly, the edited scene remains consistent across both camera viewpoints and time. 4D representations such as 4D Gaussian splatting allow us to reconstruct dynamic real-world scenes. The next natural step is editing these scenes using simple text instructions. However, directly using 3D or 4D generative models for editing is still difficult, because large-scale 3D and 4D editing data is limited. Therefore, a practical alternative is to leverage powerful 2D diffusion models. But once we use 2D diffusion models, we must ensure that the edited results remain consistent across both camera views and time. The key challenge is that 2D diffusion models usually edit each rendered frame independently. This creates multi-view inconsistency, where the same object may receive different edits across camera views. It also creates temporal inconsistency, where the edited appearance may flicker or drift over time. These are originally 2D frame-level inconsistencies. However, when these inconsistent frames are used to optimize a 4D representation, they become conflicting supervision. As a result, the final 4D reconstruction can suffer from geometry distortion, motion artifacts, and incomplete semantic edits. This slide shows the overview of Dynamic-eDiTor. We first render multi-view video frames from a pre-trained 4D Gaussian splatting scene. Then, we represent these frames as a unified camera time grid, where one axis corresponds to camera views and the other corresponds to time. Inside this grid, Dynamic-eDiTor applies two key components. The first is spatiotemporal subgrid attention, or STGA, which fuses information locally across adjacent views and neighboring time steps. The second is context token propagation, or CTP, which propagates the fused information across the entire grid. Finally, the consistent edited frames are used to directly optimize the edited 4D Gaussian splatting representation. The key representation in Dynamic-eDiTor is the camera time grid. Each row corresponds to a camera viewpoint, and each column corresponds to a time step. Instead of editing frames independently, we process local 2x2 subgrids. Each subgrid contains adjacent viewpoints and neighboring time steps. This allows the model to jointly reason over spatial and temporal relationships during the editing process. The first component is spatiotemporal subgrid attention. In a standard MMDT image editor, each frame is processed independently. STGA modifies the attention operation so that each frame can attend to image tokens from nearby views and nearby time steps within a 2x2 subgrid. This enables local feature fusion across both view and time dimensions. We also observe that applying STGA to all layers can introduce artifacts. Therefore, we apply it to a vital early layer range, which provides the best trade-off between consistency and editing fidelity. While STGA provides local consistency, we also need to propagate this information across the whole camera time grid. For this, Dynamic-eDiTor introduces context token propagation. CTP has two strategies. For overlapping regions between consecutive subgrids, we use full token inheritance, directly reusing previously fused tokens. For newly introduced temporal regions, we use flow-guided token replacement, which aligns tokens over time before propagation. Together, these strategies maintain coherent feature flow across views and time. After generating edited frames, we directly optimize the pre-trained 4D Gaussian splatting representation using these frames as supervision. The key point is that our edited frames are already consistent across views and time because of STGA and CTP. Therefore, we do not need to rely on iterative dataset update, where frames are repeatedly edited during optimization. Instead, consistent edited frames provide reliable supervision, leading to stable edited 4D rendering. This slide compares Dynamic-eDiTor with previous 4D editing methods. Existing methods often fail to complete the requested edit or introduce artifacts such as blur, motion distortion, and inconsistent appearance. In contrast, our method produces more complete semantic edits while preserving stable motion and geometry. The results show that Dynamic-eDiTor better handles non-rigid dynamic content and maintains consistency across both views and time. Quantitatively, Dynamic-eDiTor achieves the best clip directional similarity, indicating stronger alignment with the target text instruction. In the user study, our method is also preferred over baselines across multiple criteria, including overall quality, motion consistency, temporal consistency, multi-view consistency, and prompt alignment. These results show that Dynamic-eDiTor achieves a better balance between semantic editing quality and spatiotemporal consistency. The ablation study confirms the importance of both STGA and CTP. Without these components, the edited 4D scene shows severe artifacts, geometric drift, and unstable motion. STGA improves local consistency by fusing information across adjacent views and neighboring time steps. CTP further improves global consistency by propagating context tokens across the entire camera time grid. The full model achieves the lowest warping error and multi-view consistency error, and produces the most stable and complete 4D editing result. In conclusion, we propose Dynamic-eDiTor, a training-free framework for text-driven 4D scene editing. Our key idea is to represent multi-view video as a camera time grid and enforce consistency inside the MMDT editing process. STGA provides local spatiotemporal fusion, while CTP propagates context globally across the grid. Together, they produce consistent edited frames and enable stable optimization of edited 4D Gaussian splatting. One limitation is that large geometry or topology changing edits remain challenging, which we leave as future work.